Hey everyone, happy Friday. One more week to go. You guys are doing great. Keep up the momentum. I know it, and this is getting old, I'm sure, but I'm really been impressed with the effort and the commitment that you guys have had, and I really, really appreciate it. So please keep that up. I'm not going to do a loom today because we don't really need to see my face. We're just hopefully this will be short and sweet. But I do want to talk about how to write equilibrium expressions. And so the big thing when we're writing equilibrium expressions is to kind of look at it and to see what we're dealing with. We can have two different types of equilibriums, really, like a homogeneous equilibrium or a heterogeneous equilibrium. And in a homogeneous equilibrium, what we see is that we have our reactants and products are all in the same state. And so when we're looking at this, they're all in the same state. And so when we write our equilibrium expression for this, it's going to be fairly simple. Just like we saw yesterday, we can write this and we can write it like this. We can say, well, K equals the concentration of our, remember we go products first, so this would be H2 squared times the concentration of O2, right? And that would be all over the concentration of H2O squared. Now again, see, because we're looking at that, and we have our stoichiometry in front becomes our what we raise it to in our expression. All right. Now, in this particular one, we wrote it in terms of concentration. So what you'll see in the book is sometimes you'll see a C. Now that C there just means concentration. If I can spell concentration. So that just tells us that we did it in terms of concentration. So if I see Kc, right, that's not something that we're going to freak out about. It just means I did it in terms of concentrations. Now, we could also see Kp. Now, P, I wonder what that stands for. Oh, yes, you're right. It stands for pressure. Very good. All right. And in this case here, the expression would look very similar, but instead of using concentrations, we would just use the partial pressures. And since these are all gases, they would have a partial pressure inside our container, right? We learned that with gases. And so this would look like this. We would say, okay, well, the P of the H2 squared times the P of the O2 all over P of the H2O. Now, these two values, either Kp or Kc, won't be the same, but they'll be related. And we're not going to talk about how we can kind of relate them. If you take AP Chemistry next year, then you'll learn how to do that. But right now, know that you can write them in either way. They're both equilibrium expressions. They both kind of deal with how much of the reactant and product are there. We're just talking about them in different ways. One, we're talking about them in terms of pressure. The other, we're talking about in terms of concentration. We will use Kc a lot because we're used to concentration. Okay, so that's how we would write that equilibrium expression. Not hard at all, right? And so now, things change a little bit if we get to a homogeneous equilibrium. So here we have a homogeneous equilibrium where we have a solid, aqueous solution, liquid, and a gas. So this is a homogeneous equilibrium. Now, in this case here, we could just write it out the same. And but when we write this out, there are some things that we have to consider. And the things that we have to consider is that anytime that we have a solid, the concentration of that solid is constant. Okay, so solids always have a constant concentration. Doesn't matter how much I have, right? But if I think about, okay, if I take 10 grams of it, and let's say that 10 grams was in 10 liters or whatever, right? And then I cut that 10 grams in half, I'm also going to cut the volume in half. So the concentration stays constant. The other thing that stays constant is liquids. Liquids have a constant concentration. All right. And so why that matters to us is that when we write the equilibrium expression and we write that Kc for this, let's say in this case, then we don't have to include our solids and liquids into this because their concentrations are constant, and really and truly, long story short, they get wrapped into the value of Kc. It doesn't mean that they're not there during the equilibrium. They're actually still in the container. They're a part of that equilibrium because they're a part of that balanced overall equation. It just means that we don't have to include them into the equilibrium expression because their concentration stays constant. So in this case, we would just write the concentration of Ca. Let's do that again. We would write the concentration of CaCl2 times the concentration of CO2 all over the concentration of HCl squared, right? And we're not going to include that or that, right? Because really and truly their concentrations get wrapped up into that value there. And so this would be the equilibrium expression for that reaction. Okay, does that make sense? Hopefully. So I want you to practice with the book problems. If you guys have any problems with that, make sure you're reaching out via Teams. I'd love to help you and explain it to you. But if you don't need me, have a great weekend, and I'll shout at you again on Monday. All right, y'all. Peace, love, happiness. Thanks for playing.